Welcome everyone. Good afternoon. Today we are joined by Dr. Jase Bernhardt, who is the Assistant Professor in the Department of Geology, Environment and Sustainability at Hofstra University. He will be presenting today on climate change policy changes. Take it away, Professor.
Great. Thanks so much for having me on this Earth Day, of course. And I'll just be talking for a little while today about, climate change policy, how things already have been, will continue to change under the Biden administration. Also just talk some basics about climate change, what's happening, why, and what are some things we expect to see in the future, and then tie it together with the policy angle at the end. If you have any questions, feel free to type something in the chat as I'm going, and I'll get to it. Otherwise, also at the end of the presentation, which should not be too long, I'm happy to discuss questions and talk, and can definitely come off mute at that point. So again, thanks for being here, for having me, and let's get started. So actually happening right now today on Earth Day is on Zoom, just like we are, a summit of world leaders for many of the key players across the world, from Russia to Canada to China, and many other large countries, having I guess it's a webinar, really. It's since it's online, but it's a summit of some sort, just remote for everyone, where they're discussing climate policy in the U.S. So really, Biden is trying to show that the U.S. is interested in, once again, being among the leaders on climate change at the international stage. So let's talk a little bit about the basics of climate change first. Important to note the difference between climate and weather. And the key is sort of the time or temporal scale. So both climate and weather deal with the same conditions and physical variables, but the time scale is different. So they're both dealing with things like temperature in the atmosphere, and wind, clouds, and precipitation. But weather is on the scale of hours to days. Sort of think of the limits of prediction as the weather time scale. So if it's in the weather forecast or it's a current condition, that's weather. If it's beyond that 7 to 10 day time range, it's considered climate. And it's specifically an average of the weather conditions going over longer term scales of months, years, and decades. So for example, two images here, climate would be looking at the average or normal temperature for a given day. So we're giving us the context. Record highs would be a piece of climate data, as well as the hottest ever been on this day, what's the coldest. Conversely, weather forecast, or the very short-term conditions, that is weather. But again, we're dealing with the same variables in temperature here in both, but the longer term is climate and the shorter term is weather. So what's the big deal? Climate has always been changing, but it's changing more quickly than we've seen before in the current time period. And it seems like humans are driving a big portion of this. And the big cause is the emission of something called long-lived greenhouse gases. So what are those exactly? Well, greenhouse gases are gases that help promote what's called the greenhouse effect in the atmosphere. It's sort of like a greenhouse in real life. Or maybe a better, more common comparison is, think about a car on a sunny day. If you park it out in the sun, it's going to get warmer in the car than the outside, sort of the surrounding atmosphere temperature. And this is all going to work the same way. So what happens in the car, for example, is the windshield and the windows, they allow the sunlight to get through. And it's coming from the very hot sun. The energy is what's called short-wave radiation. It's a specific type of energy or radiation, transfer of energy. So that energy from the sun, that sunlight, of course, goes through the windows pretty well unimpeded, and the windshield, and then strikes the surfaces in the car and warms them up. And then the surfaces give it back off. It's a different type of energy now. It's called long-wave energy, or infrared, because the surfaces on the Earth and the car are much cooler than the sun. So it's a different type of energy coming out. And now this type of energy can be trapped, some of it, by the windshield and glass in the car. So it gives you a net gain of energy because you have more coming in than escaping out. Same thing in the Earth's atmosphere, the greenhouse effect. These so-called greenhouse gases have a special property of their structure, molecular structure essentially, that says the sunlight can get through mostly, then the sunlight gets absorbed by the Earth's surface and the ocean and everything, gets sent back up, re-emitted as it's called, but it's emitted again as a different type of energy. It's long wave or infrared. So some of that escaping energy can be trapped and bounce back down. So again, you have a net gain of energy. You have all the sunlight coming in, but not all of it escapes back out. Some of it is trapped. So of course, as you strengthen that effect, you have generally more warming as expected. There's many different greenhouse gases out there, gases that have this property. Carbon dioxide, CO2, is the most famous, probably heard of the most, mainly because it's the highest concentration, this first column here. But conversely, there's other greenhouse gases that are much lower in concentration, but they're much more powerful. As the last column here gives something called global warming potential. Essentially, how strong is it at sort of acting as a greenhouse gas? Carbon dioxide is the weakest, and then we give that a number 1. So these other gases, the numbers is how many times stronger is it than CO2? For example, methane, much lower concentration than CO2, but it's 25 times more stronger. So these greenhouse gases called methane, nitrous oxide, and what are called CFCs, chlorofluorocarbons, and these all act as greenhouse gases. They all trap some of that outgoing long-wave radiation to the surface, allowing us to warm up the lower atmosphere, aka where humans are living in the world. And notice how these gases have all gone up since the Industrial Revolution. Humans really started doing activities that put them up in the atmosphere. So the first column is the concentration before the Industrial Revolution, and then this shows in 2011. It's a little bit outdated, but it's the point stands still that they've gone up a lot now, more in the last 10 years. And where have they been coming from since the Industrial Revolution? Well, it's things like fossil fuels. So the gas we burn for cars and transportation, lots of different industrial processes, even things like land use, land coverage. You chop down a forest, and the trees do photosynthesis, which takes up CO2. Get rid of the trees, that CO2 they would have absorbed goes back up in the air. So that's another way we can put this carbon dioxide greenhouse gas in the atmosphere. So there's this big link between humans and the climate change, and the link is primarily through greenhouse gases, specifically CO2. So at the end of the day, even though it's not the strongest, most potent greenhouse gas, it has the highest concentration, so it really does have a huge impact. And here look at CO2, carbon dioxide concentration in the atmosphere for the past 60 years or so. Starting in the late 1950s, this is taken from Mauna Loa Observatory in Hawaii. So this is a good spot to sort of get a good sense of the atmosphere, because it's a tiny island chain, Hawaii, surrounded by the giant Pacific Ocean. So it's not being thrown off by like large industry nearby or something. So we see just in the last 60 or so years, CO2 level is about 310 parts per million ppm. That just means we've got a million little dots representing the atmosphere. 310 would be CO2. So it's a small percentage, but it's changing a lot. It's gone up again just in a little over 60 years, from 310 parts per million to now almost 420 parts per million. So that's about a 30 to 35% increase in just 60 plus years. And the big deal is this, it's changed before CO2 concentration, but it's never changed so quickly in such a short amount of time. So to sort of further reinforce this, here's a look back the last couple 100,000 years in terms of the temperature and CO2 concentration. You can just focus on the bottom 2 graphs. The black line is temperature, the blue line is CO2. This is taken from what are called ice cores. So in Antarctica and Greenland, this is taken from Antarctica, you have glaciers, you have ice sheets, and they slowly build up each year. A little bit of snow and ice accumulates each year. And this has been going on for hundreds of thousands of years. So you have little layers from each year, and each year when the layers of ice accumulates, it traps some air bubbles from that year inside, which means you have air bubbles going back hundreds of thousands of years just trapped in the ice. So scientists go and drill way down, a mile plus down below the surface, to get to the ice that was deposited hundreds of thousands of years ago, and you can extract it and get the air bubbles out of it, analyze them in the lab, and then get a good sense of the temperature and what was going on in the atmosphere during those times. So for example, we see this very strong connection. Temperature is higher, the black line, CO2 is higher, the blue line. So CO2 seems to be a big control of temperature changes, especially during these yellow highlighted periods, which are called interglacials. When the black line is lower, the temperature is lower, that's an ice age, CO2 is lower. And there's also occasional in-between portions, like what we're in right now, where you're between ice ages. And the ice sheets used to be much greater until about 10, 20,000 years ago, and they really retreated since then. So we're in a warmer, it's called interglacial period between ice ages. So a lot to talk about in this graphic, but again, the big thing is you see the big connection between temperature and climate change. But also notice, yes, CO2 can change by like 100 parts per million, which is sort of like what we've seen now, but it takes thousands of years. Look at the scale of this. it's 50,000 years, every little tick mark on this graph here. So changes that might take a few thousand years naturally, or several thousand years, are now happening in a few decades. So we're rapidly accelerating the pace of change here in CO2, which also means the temperature can change much more quickly than we would expect naturally. And as you can imagine, that can lead to some issues globally for human society and ecosystems, vegetation, and plant life. Here's just a look at how temperatures have been changing since the Industrial Revolution, so since the late 19th century. And what we're seeing here is one, temperature is going up, and two, it seems to be going up at an increasing rate more recently. So that is certainly a very noteworthy trend. What do we think is going to happen in the future? We use things called GCMs, general circulation models, to try to predict what's going to happen in the future, climate models. Basically, they're giant supercomputers. The Earth's atmosphere, the surface, and the interaction between the surface and the atmosphere is very complicated. So we build up a lot of equations, physics and chemistry equations, all sorts of things that explain how things work, put them all together in a giant computer program, and can say, okay, here's how the Earth's atmosphere works. So how is it going to change in the future? Well, we can drive in the initial conditions, and then how something like CO2 is going to change, since that has a big connection with temperature. So we can sort of drive in different scenarios of how CO2 might change, going up, but by how much, and then get some projections of how something like the temperature is going to change in the future. Basically, they're just splitting the climate model, splitting up the world into tiny little grid boxes, and sort of assigning a formulas and values to each grid box that give us a broader sense of how things are projected to change. And a few things to mention here with these projections is there's a lot of uncertainty, with both scientific uncertainty and societal uncertainty. So the image on the left here demonstrates the scientific uncertainty. As mentioned, the Earth's atmosphere is very, very complicated, and we still don't even know perfectly how things work. Moreover, for example, starting with initial conditions, we can't measure every square inch of the Earth's atmosphere and surface. So sort of every different type of climate model is going to take some liberties and do some slightly different things. And as a result, you have some slightly different projections. So we have different climate models that use some different formulas and equations. And therefore, you get some different results on how things might change. So this graph on the left here shows different climate models from different organizations. They're abbreviated by acronyms here, but there's some from US organizations. For example, NCAR here is the National Center for Atmospheric Research out in Colorado. GFDL is another research center at Princeton University. Hadley Center is out in Great Britain, in the United Kingdom, and other countries and organizations run models as well. It's just a sampling of a few, and notice how they all show warming, but the extent of the warming is unclear. It could be anywhere between 2 and 5 degrees Celsius, depending on sort of which set of equations ultimately end up being right. In addition to scientific uncertainty, there's also the societal uncertainty. We know we've been emitting a lot of greenhouse gas, and therefore CO2 has been going up. We don't know exactly how much more we will be doing that. Will we continue to keep emitting CO2 rapidly? Will we start to level off a bit? It's really hard to predict humans. So we just use what are called different scenarios, emission scenarios, to try to determine how much the levels of the greenhouse gases will change, and therefore how much temperature might change. So we see some different scenarios here, these different lines. Will we keep emitting more and more? Will we start to level things off? Will we even start to go down a bit? And that's going to also drive different scenarios of temperature change. Generally, what we expect is in these higher emission scenarios, temperature will go up more. Lower emission scenarios, temperatures will not go up by as much. So a lot of uncertainty overall, both in terms of the scientific uncertainty, the different types of models and equations, and also the emissions uncertainty, which is even larger. At the end of the day, there's some uncertainty with the exact equations in science, but we know temperatures are increasing. We know why. It's the greenhouse effect primarily. There's just a little bit of uncertainty with the extent of it, and certain aspects of the climate system, like, for example, how clouds might change, how precipitation might change, which, depending on how those change, the temperature changes will be different. But the even bigger uncertainty is the emission scenarios, or the human uncertainty. Because as you know, it's really hard to predict what humans are going to do. For example, the pandemic in this last year, just 2 years ago, never would have been able to predict that would have happened. It would have been so impactful. So we don't know for sure it's looking like emissions will keep going up and up, and we'll have probably the higher end temperature changes. However, maybe something will change, and for every reason, the world will get more efficient. Will be less in the way of emissions. So really, we have to just sort of use a lot of different scenarios of emissions because we're just not sure how humans are going to act. And there's some uncertainty in these climate models. Again, the big thing is what's called splitting up in little grid boxes here. Basically, the whole world is pretty big, and our computers are getting faster and faster, more powerful. But still, when you have all these equations you have to run for the whole world, you have to take some shortcuts to make it more manageable to run the climate model. So one thing we do is we split up the world into pretty large grid boxes, sort of limit the amount of detail we have in the model, which is good for allowing the model to run, but not so good for super high local precision. For example, you might say like this whole box here is all the same, even though obviously a part of it is land, part of it is water. So we're getting better and better at this, but still that's going to introduce some of that scientific uncertainty. But still, at this point, especially with the increase in computing power, we can run climate models for like smaller regions at very high resolution. For example, this particular model called the CMIP5, we can run and get a very detailed view of how might things change in New York City in terms of the temperatures. Now in a more familiar unit, perhaps degrees Fahrenheit. So it's saying, okay, right now, sort of our average years in the, for the average year, our average high temperature each day is in the low 60s. And then how are things going to change? Well, in a low emission scenario, things will change maybe only by a few degrees Fahrenheit. But in a high emission scenario, things might change really significantly, go up maybe by close to 8 to 10 degrees Fahrenheit by 2100. And if that does come to pass, that means New York City's climate looks more like Washington, D.C. or Northern Virginia. So all of a sudden, think about it, our temperatures are much different. Therefore, what can grow and live here, sort of the natural world is much different. So sort of one of the big reasons why there's a lot of concern about climate change is if we do end up going down this higher emissions, higher temperature change scenario path, in the not distant future, climate could look a lot different than sort of what we've had for a very long time in a place like New York. So what's some history of US climate policy? So at the federal or national level, there's sort of been limited amount of policy that's been put into place, partially for a lot of reasons, because climate change is often sort of looking in the future, so it's not always a priority right away, and because other things therefore take the center stage. If there's a big economic issue, oftentimes that's going to get more of the attention for policy than climate change or other environmental issues. But there have been some major landmarks, and actually it started back in 1970 when under President Nixon, the EPA, the Environmental Protection Agency, was created as sort of a central agency for the US federal national level government to enforce climate policy. And at the same time, the Clean Air Act and National Environmental Policy Act, two really important pieces of legislation that helped start maintaining things like our air quality in the US, were born then. Then in the late 1980s, under President Reagan, we have another landmark. The US and most of the world signs the so-called Montreal Protocol. That phased out a type of greenhouse gas called CFC, which in addition to helping promote the greenhouse effect and warming, also did something called depleting the so-called ozone layer, which you might have heard of before. It's a layer of ozone, that's another gas, it's O3. Sort of free oxygen in the air we breathe is O2. So two oxygens, O3, three oxygens, a slightly different particle called ozone. And ozone up in the stratosphere, up about 70,000 feet or so above the Earth's surface, is actually sort of good. It helps block out some harmful sun rays like UV radiation. But what was happening is these CFCs that we've been emitting more and more after the Industrial Revolution started were going up and depleting the ozone, creating a so-called hole in the ozone layer. So scientists eventually recognized this, and there's broad international approval to phase out the use of CFCs, and therefore the ozone layers, including the US, as part of this. And ozone layers been starting to grow back. Then in the 1990s, it became more and more clear that climate was changing, the globe is warming, and that greenhouse gases were a big influence on this. The Kyoto Protocol was a big international agreement that was signed by President Clinton However, the Republican-controlled U.S. Senate declined to ratify it. So the U.S. never actually really joined this. And then when President Bush took over, President Obama sort of formally sort of removed our support for this particular policy to try to limit global CO2 emissions. So generally, the second Bush administration was unfavorable to climate policy. The first Bush administration was actually pretty favorable to the environment. Second Bush administration, not as much, but there were some progress in the environmental realm. For example, trying to compel emissions reporting to the EPA, so companies, organizations have to report how much greenhouse gases they're emitting, in the goal of trying to understand and reduce our emissions. And also the Supreme Court case in 2007 called Massachusetts versus EPA that gave the EPA the specific power to regulate greenhouse gas emissions under the Clean Air Act, which had been passed back in 1970 again during the Nixon administration. And then in the Obama administration, there are initiatives to try and help mitigate climate change, help reduce greenhouse gas emissions and such. But generally, Republican-controlled Congress, so not a lot of action sort of firmly taken. But there was an extension of the Clean Power Plan enacted in 2015, trying to limit the amount of carbon emissions from power generation, so trying to get power, electricity from cleaner sources, which would also help improve air quality. And then, of course, Trump administration generally, not just for climate, but for a lot of policy, tried to roll back many of the Obama era policies, especially so-called executive orders. So a president can issue an executive order, but there's not really any legal requirement to enforce it. The president can sort of compel an executive agency like the EPA to enforce it, but then when the next administration comes in, no matter their political views, they don't have to feel at all obligated to continue that because it's not really on the books of the law. So many of Obama's executive orders Trump did not follow, just like the Biden administration isn't going to follow the Trump executive orders. And that those are frequent, especially when there's sort of a disparity between the party of the president versus the party of Congress, especially the Senate, but also the House as well, because a lot of times we know that if Congress is one party and the president's the other, Congress may very well act to block an actual law getting put on the books. The president can issue an executive order that has some power, but again, the next administration could sort of choose to ignore them. That often happens for a wide variety of issues, including climate change. So state and local governments have also done some climate policy. This is, of course, very widely between the political views, very widely between states. Therefore, their action on climate has been more or less aggressive in some instances. Some states and cities, counties issue reductions in greenhouse gases, targets for reducing them, but generally they're non-binding, so it's more just sort of goals and not actual like firm laws. And again, the national administration or just another administration for that level of government can sort of come in and say we're throwing those goals out the window. Back in 2016, Washington State tried to pass a carbon tax for the state, but it was defeated pretty soundly. Actually, both sides, both the left and the right, were against it for some different reasons. There is a sort of less restrictive plan in place called cap and trade that several states take part of, including New York and many Northeast and Mid-Atlantic states take part in something called RGGI, the Regional Greenhouse Gas Initiative. And that sort of acts to sort of create incentives for firms, companies to limit their CO2 emissions, but it's not quite as aggressive as straight up taxing them on carbon emissions. And again, the blue states here are in the so-called RGGI agreement in the Northeast. Also, California and Washington State have their own what's called cap and trade plans. Essentially, it's called cap and trade because you're sort of capped to a limited number of emissions. Then you do get taxed if you go over that cap. It's not a pure tax if you go over your limit. And then the trade part says, if you go below your limit substantially, you can sell your allotment to another company at sort of a lower level than the tax would be, and then everyone wins. You make some money for being efficient. The other company pays less than they would have to on the tax. So it sort of therefore can sort of cap or help limit CO2 emissions and sort of encourage everyone to get more efficient. So again, not quite as aggressive as a straight up carbon tax. All right, so what are some expectations and thoughts? and what's been happening already with the Biden administration, they've certainly been placing a very strong emphasis on climate, which is sort of a departure from normal, because as I've mentioned, during times of big national security issues right now, the pandemic and the related economic challenge, or when there's an economic downturn, there's often a lot of attention being paid to those issues. Climate and the environment takes a back seat. But really, Biden is seen today with this summit among world leaders that the U.S. is leading on Earth Day. Clearly, the Biden administration, despite all the other challenges, is putting a lot of energy into fighting climate change and trying to reduce our impacts on the environment. However, it's hard to get long-term laws in the books. For example, now we do actually have the administration and both chambers of Congress, for now at least, are controlled by the Democrats. It's quite rare and very well could change in 2022 in the midterms. But of course, the Senate is just by one. So as we're seeing, a lot of these aggressive policy maneuvers being proposed by Biden, maybe even passing the House, might not necessarily get passed in the Senate because the more moderate Democrats might not necessarily vote for it. So we'll see what happens. Again, those sort of the long-term laws, especially when climate gets caught up in other big spending bills, there still seems to be difficulty in getting long-term laws passed. Biden administration is calling for a 50% reduction in greenhouse gas emissions by 2030, which is quite aggressive. We're right now sort of in the 10 to 15% range currently. So to get all the way to 50% in less than a decade seems like a challenge, but that's at least going to be the goal they're going to call for. And there's been calls, Obama administration had similar calls. The Bush administration was favorable towards trying to reduce our emissions. And of course, at the state and local levels, lots of places are calling for reduction. Generally doesn't happen, but it's sort of seen as at least an encouragement to start that conversation, get things down. The ultimate goal is to have carbon neutral, so no net emissions by 2050, which is obviously even more of a aggressive thing to try to do. So we'll see. But part of this is, even if the U.S. can't quite do it, is just sort of trying to show the world we're more serious about it. The U.S. under Trump pulled out of the Paris Climate Agreement, which had been signed just before his presidency started, and U.S. has joined back in. That was one of Biden's things in the very beginning of his term. And in addition to sort of just rejoining, the U.S. is also trying to show they're serious by calling for these big cuts in emissions. Of course, politics, you have to get a lot of parties on board, and many of them might not be very willing. For example, large corporations see this as a burden because it can lead to extra costs associated with getting more efficient or paying taxes on carbon if those laws come in place. And of course, it means a big change in our energy extraction and distribution systems, which can be costly and maybe lead to more jobs in some places, but fewer jobs in other places and industries, which is always going to be looked at unfavorably by some people. And the general is economic concerns with climate. Big climate action leads to a lot of hesitancy. Overall, there's general support for climate action in the U.S., but interestingly enough, opinion has actually been fairly stable over the years. And here's just some graphs of climate views over time, looking just between 2008 and 2018, so a recent 10-year period. These different lines here. So first on the left showing beliefs on climate change. Is it happening? Yeah, most people agree it is. And more people agree it's caused by humans. And that scientists agree on it, but you see it's only been sort of a modest tick up. And if you look at the period as a whole, it's just been a very slight increase in sort of beliefs. Similar with policy support. You see that actually beginning here in 2008, there is pretty broad support for more research into renewable energies, which can limit our CO2 emissions, and general support for regulating CO2. Then you see it actually went down, and perhaps part of that is due to the economic downturn, 09, 10 especially, sort of people realizing maybe more important is focus on the economy, and if climate regulations will hurt the economy, then we don't want that right now. And it started coming up as the economy has improved, perhaps. But overall, sort of net change over the period, we see it's pretty flat. Sort of policy support has been there, but it's not necessarily increasing. Maybe in recent years, it's gone up a bit more now, but not overall prior to that. So sort of summing things up, as you can gather, climate policy is very challenging to implement. Overall, there's public support, but people also tend to prioritize other issues, from the economy to social justice and all sorts of other things, things that are seen as more pressing. So that's why we've had some action on climate. There's calls for more, but still, when push comes to shove, there actually isn't a ton of strict regulations right here in the US right now, as we speak. All right, so that's all I have for the presentation, but I'm happy to answer any questions, discuss any of these things further. So feel free to ask if you have any questions.
I'm going to stop the recording now, and then we'll go into questions.
Thank you.